Hello, hello, hello. Testing one, two, three. Hello, hello, hello. Testing one, two, three. That'll do, I think. Cool. Yeah, I was so annoyed with myself for doing so many mistakes last time that I thought I'd go buy some chilies and use them as punishment for when I make a mistake. So I actually quite like these ones, though they can get hot, but I don't like the bitterness of these, so I think I'll start with these ones and I'll progress as I get better. It still makes some mistakes, but I'll have some of these. And then I've got a reward when I finish this 1.3.1, which I'm going to go revisit the question. I've kind of laid out some basis, the boring part. I just want to go through it one more time, see how I understood it, and uh, and punish myself as I go along. I've only got the four chilies. I've got some more in the fridge, but goodness sake, like, can I really make that many mistakes? So hopefully a little reward system will improve my quality of thinking. So let's get to it. Actually, I just lost my pen. There it is. I've got my pen again. Um, if we remember back to the exercise, it says form an orthogonal basis in two dimensions, starting with these two vectors. And can you generate another orthonormal basis starting with these two vectors? So form an orthogonal basis in two dimensions. So this is what we did last time, but I've kind of recapped here. So we've got the two vectors here, and I'm going to imagine that I and j are equal to this. So we can calculate the actual vectors themselves. A is equal to this, b is equal to that, because we have multiplied the the coordinates, the vectors by these coefficients, and then we can calculate the orthonormal vector. Um, this 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 is a bit too far down the line, so let's start with the orthogonal actually, because I think this is probably not where we want to start. In fact, that's why I moved it down. I got a little bit ahead of myself, so let me just move that down for a second, and let's also erase this 2 here because that's not right. Um, right, so I'm gonna have to be really careful here, essentially, because I don't particularly want to eat a whole chili, but I do enjoy eating chilies, but not just on their own. So let's see how we go. So we calculate the vector. The next step is to, if I remind myself, it's the reciprocal, the negative reciprocal is the is our vectors orthogonal to vectors. So let's start with that. So we calculate the negative reciprocal. So actually let's make this super clear as well. I want this to be like a kind of a sheet where I can go back and go, oh yeah, that's what you do, right? So I'm going to move this just along a little bit so I can mark the things accordingly. And also, I'm going to color these things in as well. So I'm going to go for a purple here. No, let's go for something a bit nicer, a bit sexier. There we go. Oh yeah, and that's going to be the 4 times j there. So the vector A is equal to that. The vector B is equal to this. So it says form an orthogonal basis in 2 dimensions, starting with this, an orthogonal basis. So the way I'm going to start is just to remind myself that we can actually create an orthogonal vector. So let's say this is um, a AO, and that is going to be 0 and 3 is the reciprocal, and we can do the negative reciprocal here like that. So if we were to just prove that that's the case, it should be that Uh, and let me put this as a little kind of grey, or maybe I don't know. Let's go for some purple. Fine. We'll say 0 times 3. Um, if I remember correctly, it had to equal 1. So actually, in this case, it won't ever equal 1. Um, yeah, let me go think back to this because I'm not entirely sure I remember. It says the dot product of A with itself, dot product of B and A. That's fine. We're talking about the reciprocal here. Um, well, perhaps, I've done the following. Please assume all lesser vectors. It asks form an orthogonal basis in 2 dimensions, starting with that. So I started with assigning I and j because I know these are linearly independent. Then I added the equations together. 3, 4. I then took the negative reciprocal of this. So I think so. What I've had to do there is go. Um, let's move this down a little bit. And I think it's not this one. Um, it's the orange part and the blue part. Here we go. So let's do that, and let's do this. And so A actually equals um 3 plus 0 and 0 plus 4, which equals 3, 4. Now that's more like it, isn't it? Okay, so now we calculate the negative reciprocal is actually going to be, let's call this A orthogonal, right? And so it's going to be, the reciprocal is going to be 4, 3, and then the negative is to make it a negative reciprocal, or in fact we could have done that apparently. Right, and then I guess that's what we're going to calculate here was that if we do 4 times negative 3, and let's see what I do here. So I go, um, from the equation you've given, it says A over B times B over A. So 4 times 3, no, 4 divided by 3, sorry. 4, let's start with this. So 3 divided by 4 times 4 divided by 3 should equal 1. And so let's do that. Let's say 3 divided by 4 is a little tricky, I guess. So let's try that. 3 divided by 4. 3 divided by 4 is 0.75. 3 divided by... Oh, that's so interesting. I guess that does make sense. Okay, 0.75, okay. So that's 0.75 times and then 4 divided by 3 is going to be 4 divided by 3 is equal to 1.3 recurring, right? Let's put 1.33 recurring just to be absolutely clear. And so if I times that by 0.75, we get 1. Okay, it's just nice to put that there just so I remember it as a concept. And if you were to do it the other way around, that shouldn't make a difference. Now let's do 3 divided by 4 times 4 divided by -3. Of course, this will equate to the same output but negative, right? So this should be -1. This should be. I'm not saying I've done it. Let's just double check. So if I do 3 divided by 4 is 0.75 times 4 divided by -3. Let's do it again. 4 divided by -3 equals -1.33, and so of course that would equal -1. And then if I'd done it the other way around, so let's put this in red. If I'd done 3 divided by 4 times -4 divided by 3, we will get something a little wild, I guess. So let's do that. So it's going to be 0.75 times 4 divided by -3, which is silly me. -4, sorry, -4 divided by 3 is going to be -1.33. Oh, so that actually doesn't matter. Good. Okay, that's good to know. So I've cleared that out in my head. So actually, this is totally fine. In fact, this can probably be written in purple as well. I think I'm going to do that. Just going to put a little box around this to make it clear for myself. Like that. And then we'll do the last one, which will be the wrong one, yeah? So let's go 3 divided by 4 times -4 divided by 3 is equal to -1, because 0.75 times -1.3 recurring is equal to -1. So I guess the thing I was doing yesterday, or the day before, whenever it was, 0.75 times, was doing both of them negative. Because if I saw that the way to express it was to have this negative before the fraction, right? So it's now good to remind myself that it doesn't work. -4 divided by -3 will equal 1.3. That's correct. Okay, so now that's wrong, because that's going to equal 1. So times 0.75 equals 1, which is wrong. Good. Okay. So we know why that works then. And so for -3 is an orthogonal vector, but form an orthogonal basis in 2 dimensions. So the thing that's intriguing is that I feel like So if we go back to our graph here, let's see, we had um, 0, 0, 3, 4, and then 0, 0, 4, negative 3. Do these form a basis? Is a question I'm not so sure about. I'm just going to refresh this page one sec, see if they've corrected that bug from yesterday. It was really slow. Perhaps they haven't. So to be clear, is 3, 4 is A equals 3, 4 and A orthogonal equals 4, negative 3, or R AO stands for A orthogonal. To be clear, is AO, and then if we go back to the question, it says form an orthogonal basis. Is AO an orthogonal basis, or is it simply just an orthogonal vector? A basis is something that is in a set of bases linearly independent, but in the case of these two vectors, one can use use A and apply negative reciprocal rules to form AO. Does this still count as an orthogonal basis? Have I missed the point? Let's try that. Oh, it's generating already, but it's not come up with the arrow. Okay, it says, let's clarify the terminology and concepts. Orthogonal vectors. Two vectors are said to be orthogonal if their dot product is 0. For 3, 4 and 4, 3, the dot product is indeed 0, which confirms that they are orthogonal. Agreed. An orthogonal basis, a set of vectors that are orthogonal to each other and are non-zero forms. A set of vectors that are orthogonal to each other and are non-zero forms forms an orthogonal basis. A set of vectors that are orthogonal to each other and are non-zero forms forms an orthogonal basis for a vector space. Each vector in this basis set is orthogonal to all the other vectors in the set. So given that the question actually notes a second vector, b equals 2i minus 6j, I assume that my new vector, which is simply the reciprocal of A, is not actually now forming an orthogonal basis because the new vector is not orthogonal to both A and B. There you go. So I think that was something I wanted to clear up in my head, and so this is good to exactly. Given vectors A and B, if you want an orthogonal basis, both vectors in the basis need to be orthogonal to each other. the vector A that you found, which is orthogonal to A, might not be orthogonal to B. Hence, you can't consider A and B uh, 0 to be an orthogonal basis with respect to both A and B. To form an orthogonal basis from A and B, the Gram-Schmidt process is one of the standard methods. Okay, this is more like it. The procedure effectively corrects the second vector and third, fourth, etc. for higher dimensions to ensure that all vectors in the basis are orthogonal to each other. For R2, two-dimensional space, with vectors A and B, start with vector A, find the projection of B onto A, let's call this projection P, subtract this projection from B to get the orthogonal component of B with respect to A. This orthogonal component, along with A, will be your orthogonal basis. So the formula for the projection of B onto A is the dot product of B and A divided by A times A. This is it. So we've come to that conclusion. So let's just rub this out. And our summary here is that for although we have formed an orthogonal vector to A, it is not necessarily orthogonal to both A and B. Therefore, we need to use the Gram-Schmidt process. Right, that's good. That's a good bit of learning, that. I'm just going to eradicate these dots. Good. So now let's go on to the Gram-Schmidt process, and I think what we'll do is we'll take this part again, and then we'll work with that. You know what? I can't do it here, so let me just do it like this instead. Copy that. I'm going to go over to here. So you're going to try and keep level as well. Paste that in there, like so. And then I'm going to do my dots again. Here's a dot. There's a dot. Everywhere's a dot. I can't see that dot yet. There it is. Okay. So now with the Gram-Schmidt process, Gram-Schmidt. Is that the name? Gram-Schmidt. Okay. Theorem. So what we're instead going to do is it says the projection. The projection of B onto A. And actually quite liked the way they wrote it last time. So let me just proj A onto B. Proj A onto B is equal to B A divided by A. So we now need to do B. Let's do that then. If I just separate these out like this. Oh, wrong color. Let me try that again. Oh dear. It's a bit difficult. Oh no, what's going on now? Okay, so let me do it now. Good. Let me just make that a bit smaller. Because my laptop screen is not gonna fit this on otherwise. Okay, so let's do B now. So this is where I fear the chili peppers. So B equals, I think these are is it bird's eye chili or Thai chili, something like that. think so. So b equals 2 times I is 1, and then 2 times 0. So that's going to be, that's the orange bit. I guess it's going to be over here. Equals 2, 0. 2 times 1 is 2, 2 times 0 is 0. Okay. And then I want to do the blue bit. Let's go and get my blue, which is this. And this will be 6 times j. So 6 times 0, and then 6 times 1 equals 0, 6. And therefore, b is equal to 2 plus 0, 0 plus 6, which equals 2 plus 0 is 2, 6 plus 0 is 6. And what I'm going to do is I'm going to highlight these. These are pretty important. Okay. So now we do our projection, which I'm probably going to muck up. So here we go. So to do the dot product here, we do. It's going to be 2. We're doing 2, 6, and 3, 4. So it's going to be 2 times 3 plus 2 times 3 plus 6 times 4. So that's 2 times 3 plus 6 times 4. Well, I don't really need that. That's silly of me to do. Which is going to equal 2 times 3 is 6 plus 6 times 4, 6 fours, so it's 6, 12, 18, 24, 6, 12, 18, 19, 20, 21, 22, 23, 24, yeah. 24, which is going to equal 30 over, now the dot product of A, and also this also needs to be multiplied by A, right? So let's put this the other way around, I guess, because it's a bit ugly with that at the end, I think. A, like that. So we're going to do this top part first. So let's put this as orange, I guess. And then we'll put this part as blue. Okay. So that is going to be 3 times 3 plus 4 times 4 equals, because it's this times itself, so it's 3 times 3, 4 times 4, 3 times 3 is 9, and 4 times 4 is 16, which equals 25 is this? 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, yeah. Um, Now, let me just double check this over before I eat a chili. Uh, um, B is 2 and 6, so B is 2 and 6, so 2 times 1, 2 times 0, 6 times 0, and 6 times 1, so it's definitely 2, 6, and then, so B times A is going to be B is is 2 times 3 and 6 times 4, and then 6 plus 24 is 30. Good. 3 times 3, 4 times 4, 9, 16. Yes. And so then okay, let me just highlight these. And so then let's do equals that, but then I guess it kind of leads on to this. And so A, 30 divided by 25, A is 3, 4, 30 over 25, which equals what's 30 over 25, I wonder? 30 divided by 25 equals 1.2. 3, 4, 1.2. And therefore, well, actually, this is fine. And then so this will equal 3 times 1.2 and 4 times 1.2. I think we'll just eradicate these, actually, they're not that helpful. Which equals 3 times 1.2, 3.6, and then 4 times 1.2 is going to be 2,468, so it's 4.8. Okay, let's imagine I got that right. So this is the next part. Projection A onto B is equal to that. Let's see, because I think oh, yep, we did it wrong. Ah, we did it wrong. It was supposed to be negative. There's my first chili. Okay, are you ready for this? This is supposed to be negative. I've done it wrong again. Here we go. Oh. Maybe it's not too hot. It is kind of hot. It's kind of hot. Oh, it's definitely a punishment. Oh, she's growing. Oh yeah. Oh no. Whew. Okay. Oh man. I don't know if you can see it, but I'm sweating. So we can get an extreme close up of this. It's only a bird's eye chili, but oh wow. Okay. Cool. Right. Moving on. Oh, it's really. Ooh. Okay. Cool. Let's not do that again, eh? Let's not do that again. One sec. Okay. Oh, it's been a while since I had a chili like that. Whew. Let's beaver through. So a mistake here is I forgot my negative. Oh, I can barely hear anything now. Ah. Okay. So I've got to do this again. It's um it's two. It's negative six times zero, which is zero. Then it's negative six times one is negative six. Ah, and then so this will now be negative six. Zero plus negative six is negative six, and then it's zero minus wait. Okay. So it says oh, okay, maybe this wasn't a good idea. I can barely focus now. Well, let's not do that again. Oh my god. Don't make another mistake, James. Oh, I hate the green ones. They're so bitter. It's just not pleasant. The red ones are a nice flavour at least. They're still hot though. Okay, let's focus down. So b is equal to 2 plus 0 because it's 2 times 0. So it's not even plus here. Oh yeah, okay, see, because we're plusing them together. So it's actually going to be negative 6 times 0 and negative 6 times 1, 2 plus 0, and then it's actually 2 minus 0 minus 6 here. Minus 6. Yeah, um minus 6, yeah. 2i um 2 times 1, 2 times 0, 6 times 0, negative 6 times 0, negative 6 times 1, negative 6 times 1. And so then we want to negate them, so it's 2 take away 0, 2 take away 0, and then 0 take away take away 6. Yeah, 2 negative 6. So let's go back through this. Um, it's going to be 2 times 3, it's correct, but it's negative 6. Plus minus is minus. It's going to be negative minus 6 times 4. Well, actually, no, it's not. It's plus negative 6 times 4, which is going to equal 6 plus 6 minus 24. Um, 6 times 4 is 24, but it's negative 6 times 4 is negative 24. And then it's going to be 6 minus 24. 6 minus 24 is I'll be getting this. It's going over now. We've got a peak. It's not long enough to be horrendous, but it's quite a sharp, vicious sting from a bird's eye, isn't it? Quite a bit surprising that was. I forgot how hot these things are. Yeah, so 6 take away 24. Take away 10, we get to. I'm just so bad at addition. 6 take away 24. 6 take away. I can't think. I literally can't think. Let me just check my blood sugars. Oh, no excuse there. You know what? Let's just not waste time. 6 take away 24. Negative 18. Okay. So this is wrong. This needs to be negative 18. I think I just want to double check one more time. We're going to have 2 times 3 because b is 2 on this one. 2 take away 0 is 2. And then times 3 because a is 3. Yep. Okay. And then plus negative 6 times 4. So this one here though, it's 2 times 3, and then it's actually it's 2 times 3 and then negative 6 times 4. That's correct. And then it's 3 times 3 and 4 times 4. 25. So let's do that. Negative 18 divided by 25. I think I may have gone wrong again somewhere, but that's okay. I'm still thinking about this. Negative 18, 25, which equals negative 0.72. And then 3 times negative 0.72, 4 times negative 0.72 is equal to let's have a look. 3 times negative 0.72, negative 2.16, 4 times negative 0.72 equals negative 2.88. I think I might have gone wrong somewhere here. So I'm going to go over it. I don't count this as a fail because I'm actually trying to think through this first, catch my error before I actually commit to it. I've got let me use the mouse here. Let's look up here. It's a bit more interesting, I guess, to watch. So I've got 2 times 1, and then 2 times 0, 6 times 0, and negative 6 times 0, and negative 6 times 1. Naught, negative 6, 2, 0. And so to add them together, or to take them away, sorry, it's 2 take away 0, and 0 take away 6, 2, negative 6. So this looks correct. And then we go b times a, or b dot product of b and a is 2 times 3 plus negative 6 2 times 3 and negative 6 times 4, and that is going to be 6 times 6 take away negative 24 equals negative 18. Then 3 times 3 plus 4 times 4. 3 times 3 is 9, 4 times 4 is 16. So we've got 9 plus 16 is 25. And then we've got the 3 and 4 times negative 0.72. So let's just double check that. So negative 18 divided by 25, negative 0.72. So maybe this is saying 1.2. So it says 0.6 and 0.8. 2 times 2 and negative 6 times 0.6, 0.8. So I wonder where 0.6, 0.8 came from. Because this one is saying start with vector, find the projection of B onto A. Let's call this projection P. Subtract this projection from B to get the orthogonal component of B with respect to A. So this feels right at the moment. So I'm gonna commit to this. 3 times negative, yeah, okay. Let's commit to that. And so then we so where does it say that in here is the question, because I don't really remember it. So it says, let us now take up the ground truth procedure for converting a linearly independent basis into an orthonormal one. The basic idea can be seen by a simple example. Imagine a two-dimensional space of vectors in a plane. Let us take two non-parallel vectors, which qualify as a basis. To get an orthonormal basis out of these, we do the following. Rescale the first by its own length, so it becomes a unit vector. So this is slightly different, right? Find the projection of A onto B is a different thing. So let's try and let's try finish this one off, and then we'll do the other way. It says subtract this projection from B to get the orthogonal component of B. So I guess let's do 1, and then 2 is A orthogonal, or let's say C is equal to let's say P equals P projection from B. Subtract this projection from B. B minus P. Okay, so B minus P is equal to 2 minus 6, take away negative 2.16 negative 2.88, which will be equal to 2 minus 2.16 is negative 4.16, and then negative 6 take away so it's 2 minus minus 2, so this will be, yeah, 2, this is the difference, isn't it? It's 2 minus minus 2. 2 minus minus 2.16 equals positive. And I wonder as well over here, if I do 2, or if I do 2 minus 6, you get negative 4. But if I did 2 minus minus 6, or 2 minus, it's just 2 minus 6, isn't it? Yeah. Okay. Yeah. So I could have actually, up here I could have just done 6, right? So and then at the end I just do the takeaway, right? So actually I think I prefer that technique. So if I do, it's 6 times, yeah, I think this is much nicer. Let's do that. Then it's 2 minus 0 and then 0 minus 6, and that makes much clearer the problem here, I think. Good. And in this case, it really is negative 6 times 4, and we are plussing them together, and a plus and a minus equals a minus, so that's okay. So this one, 416, then I've got it's negative 6 um, negative 6 negative 6 take away negative 2 point, wait, where's the 2.88 come from? I can't remember. 2.88 is, it is 2.88, okay, fine. Negative 2.88 equals negative 3.12. So let's see, I think 4.16 negative 3.12. So we got there in the end with that projection anyway, without even the 0.6 and 0.8. That's good. So this becomes a new vector, 4.16 and negative 3.12. So let's see this then. Let's go and add another table. Let's make this blue, and we'll give it lines. And then I'm going to go 0, 0, and I'll do 4.16 and then negative 3.12. And sure enough, look at that. Now, it doesn't look orthogonal to both of them because that's not even possible, right? But if we took the dot products of them both, we should get 0. So let's now go and qualify that this was right. Or actually, let's call this 1. Now let's try the second way round, right? So this book has said first rescale the first by its own length. So here's the vector, and you divide it by the length of I, and the length of I is the dot product of the two, and you square root it. So let's yeah, let's move over a bit, and I'll go over here. So if we follow this, no, 1 equals I divided by the magnitude of I. So this is like an idea, right? We need to remember this is the idea, whereby where I, the magnitude of I, is equal to the square root of the dot product, or the inner product of i's. So that's our little reminder. Now, if we do that, then if we take A is equal to 3, 4, so 3, 4 divided by and we got the inner product here, I think we did. That is 25 is equal to, well, it's the squared as well, isn't it? No, it's not. It's 25, okay. Now let's see if we can work this out, because I don't know if this actually works out. 3 divided by 25, 4 divided by 25. Let's try that. It's equal to 0.12, and 4 divided by 25 equals 0.16. So now we've got our we've got the first part of that, and then it says the first basis vector. Rescale the first by its own length, so it becomes a unit vector. This will be the first basis vector. So I'll call this 1. Get first basis vector. 2. Subtract from the second vector its projection along the first. Leaving behind only the part perpendicular to the first. Such a part will remain since by assumption the vectors are non-parallel. And so subtract from the second vector. So we have our second vector is 2, negative 6. So 2, negative 6 subtract from minus subtract from the second vector its projection along the first. And Let's just remind ourselves what the adjoint is. I actually can't remember. Adjoint. Define adjoint. Relating to or denoting a function or quantity related to a given function or quantity by a particular process of transposition. Um, the adjoint is uh, sorry, this one, sorry. So, and this should be the square root, shouldn't it? So one first get the basis vector, which is 25, and it's the square root of 25. Um, so this is not quite right. It's sorry, the laptop's broken or crashed. A second. We're going to come back soon. Bear with it. There we go. We're back. Oh, actually, I can't undo. Let me just refresh. Can I even undo it all? No, I can't. Bear with me. I just need to restart this notebook. Okay, getting there. So it's 25, but it's actually the square root of it that we wanted. And it's interesting because we have here the projection of A onto B does not take into account the square rooting. So that's interesting. But so if I go back over here, you see this projection A onto B, it does not deal with square rooting. In fact, it doesn't care at all about it. So let's try this with the square root, like the book's telling us. And so the square root of 25 is equal to 5. Oh no, it's gone wrong again. Gonna work now? Yeah, okay, cool. So 3 divided by 5. 3 divided by 5, 0.6, and then 0.8. Just going to check it for 4 divided by 5, 0.8. So that's where we got our thing before, I see. And now if we take that away from 0.6, 0.8, so it says subtract from the second vector. So we've got the second vector. We're going to subtract from it its projection along the first. So this actually ends up being the projection. Get first basis vector projection. Which is interesting, isn't it? So let's look at that in terms of. Can I just hide these? Is that possible? Yeah. Okay. So if I go here and do another table, and I go 0, 0, and then I put in the first one, which is is it 4, 3, or it was 3, 4. Oh, it keeps crashing. 3, 4. Okay. And then let's make that line. And then let's go for a second table. And this will be 0.6, 0.8, and then it was so that's normalized. Okay, I see, I see, I see. This talks about squaring, but I don't think we got to that yet, have we? So it's saying that the inner product, so clearly the inner product of that new one is going to equal 1. So I guess it becomes a unit vector. As for the second vector in the basis, consider 2 equals 2 minus that 1 times the inner product of those two. So it says subtract from the second vector subjection, leaving behind only the part perpendicular to the first. So now if we go and plot this final one, table, yeah, green's fine. Let's do line 0, 0, and that's going to be 2. Actually, let me just double check this because I think the -6 I may have missed here. So no, no, that's fine. That's fine. So 2 take away 0.6 equals 1.4, and then it's going to be -6 take away 0.8, -6.8. Let's plot that and see what happens. 1.4, -6.8. And so this says leaving behind only the part perpendicular to the first. Subtract from the second vector its projection along the first, leaving behind only the part perpendicular to the first. Such a part will remain since by assumption the vectors are non-parallel. Rescale the leftover piece by its own length. So if we go to the next part, rescale it by its own length. Aha, this one here, yeah, I see. So this is actually the second part. So let's just move this down a bit. And we'll do another cloudy. So we'll go 2 equals 2, sorry, minus 1 times by the inner product of 1 II. So that's a little cloudy. And so this is what we've got here, right? We've got 2 is equal to, in fact, let me just do that, is equal to, so 1 is equal to this, and then 2 is equal to that, which I'm not sure if that looks right yet. 2 times, no, 2, and then you take away 0.6 is 1.4. That makes sense. And then -6 take away 0.8. I mean, it is right. -6 take away 0.8. Yeah, that is right. Yeah. And then we've got to multiply this together. So it's this times by maybe I can make this up a bit. 1 second. So it's 2 -6 minus 0.6 0.8 multiplied by the inner product of 0.6 0.8 and then 1.4 negative 6.8 equals, and that's going to be no, because we've got a second vector here, so we actually don't want to do that. It's actually it's not that. It is actually 2 and 6, 2 and -6, 2 -6. That's it. Yep. Okay. So let's just put a little arrow here, and we'll 1.4 -6.8, 1.4 -6.8, and so it's going to be, whoops, I need to chuck my pen across the desk. It's going to be 1.4 -6.8 times times the inner product of this. 1.4 -6.8. Okay, right, we're getting there. And so let's do this one next. So this inner product, let's do that next. I actually don't know how to do it. Here we go. No, I don't know how to do it. Let me do it from here. Gosh, not quite. Let's just copy this whole thing. Oh dear, that's not very good, is it? All right, well we'll redraw it all out then. Fine. 0.6 times 2 plus 0.8 times -6 equals 0.6 times 2 is 1.2 plus 0.8 times -6, I don't know. 0.8 times -6, -4.8, which equals 1.2 take away -4.8, 1.2 take away -4.8 equals 6. So it's now 1.4 -6.8 times 6. This is 6.4 -636.8 oh, okay. Yeah, of course, yeah. That's fine. 40.8. That's why I did it. I was just like, that can't be right because I got the 8s in there. It's not 10. And then 6 times 1.4 is not that either. 6 times 1.4, 8.4. Yeah, that's more like it. Okay. So let's try that instead. Let's add another table in here. That's fine. So sorry. That chili is just wearing off now. Quite interesting actually. 0, 8.4, -40.8. Let's just hide this for a second and hide the purple, hide the red. I see. I need to go back onto this one. Yep, and then make sure it's a line. Okay, she's quite big there, so I think maybe I've probably gone wrong or something. Let's just double check through that. So it says to subtract from the second vector the projection along the first. So we've done that. And then we such a part will remain since and then rescale the leftover piece by its own length. We now have the second basis vector. It is orthogonal to the first and of unit length. Oops. So not quite. Not quite, because that is not orthogonal to the first. That's definitely not orthogonal to the first. I mean, we can prove it, right? But first let me just double check these things. So it's 2 minus 6 take away 0.6 and 0.8 because these ones, and I think we had 0.6, 0.8 somewhere. 2 times 6 negative 0.6 times 2. Yeah, that's it. Yeah, I think I've done this part wrong, right? This is wrong. Can I undo? Oh, I can't undo still. I think the actual software's gone wrong. One sec. Let me just restart this software. Shame. I might have to go to something like the Google product because clearly I'm just trying to whiteboard something. Why is this like buggy? Unbelievable. You'd think such a simple tool would be solved. Ain't bloody protein folding, is it? Shame. Alright, see if I can undo now. Nope, I can't undo anymore. What has gone wrong with this? How did I make that work? Yeah, now it's working. What? Try that again. Now it works. No idea. Okay, fine. Right. Um, what are we doing? I've totally lost my track now. Yeah, so 2 times 0.6. 2 times 0.6 is 1.2. Ah, that's where I went wrong. 1.2. But how did I go wrong to 1.4? 2 times 0.6. Yeah, I think I just made a mistake. It's just another mistake. I cannot believe that. Ah, for goodness sake, how can I get such a simple thing wrong? Before I eat this, I want to just focus on this next part. Negative 6 times 0.8. What is that? Negative 6 times 0.8. Negative 4.8. Where did I go so wrong? Oh, no, no, hang on. Hang on. It's takeaway. Everyone calm down. It's 2 takeaway 0.6. That's better. 1.4. Okay, right. Whew. Negative 6 takeaway 0.8 is negative 6.8. That is correct. So why is that saying the inner product of that is... This is slightly different. This is why. Okay, so I don't need to look at that. So let's find out if this is actually working then. So if I now go to do the inner product of um, these two vectors, so well, 1 and 2, let's just do a kind of dividing line here, I think, or maybe 3. Here you go. It should equal 0, right? So this has not worked. No, no, okay, I see. So, okay. Right, so this is the next one, which is 1, 2. Oh, 2 prime. Interesting. Let's call this 2 prime then. Is equal to 1 I minus, let me just do a blood test. Still looking good. Still I feel a little bit wobbly, but anyway. 1 multiplied by 1 2. So I think we've got quite a few of these components already. And I guess I'm just going to move this down a little bit so I don't lose everything. Maybe like that. And I'm going to do the same here basically. So 1 is 0.6, 0.8, And then 2 is 8.4 negative 40.8. And maybe I've done something wrong here actually. So if I'm trying to do 2, which is yes, 2 minus 6 take away. Yeah, this is wrong. This is all wrong because I did the takeaway first, and I think I've done that before. So let me just absolutely be confirming here, but I think that's where my mistake went wrong. Uh, it's actually this. Um, yeah. Okay, there you go. There's my next chili. Oh God, I cannot believe I've done that. And you waste so much time doing it as well, which is such a shame. Yeah, it's wrong. What else can I do? It's wrong. Oh God, guys. Why have I see, I'm just such an idiot. I've got to learn not to do this. This is it. This is the punishment for being such a bloody idiot. You see, I've taken it away before I've multiplied. What a fucking idiot. Ah, here we go. Oh God. Here we go. Water. Oh, that was so bitter. Um, it's a little hot. It's a little hot. It's getting hotter. Remember BODMAS. You are eating this chili because you forgot BODMAS. You fucking idiot. Okay, it's getting hotter now. Here we go. Here we go. Oh, oh goodness me. Ah! Remember BODMAS. So have to do this again. The last one was the negative. I won't forget that one. Don't forget the negatives. Don't forget BODMAS. Whew. Oh yeah, this one's hot. This one's really hot. Oh. Oh goodness me. That is really hot. Oh, oh dear. Ah. Don't forget BODMAS. Oh, it hurts to speak. Whew. Ah. Oh man. Oh no. Oh no. It's all coming now. Ah. Don't forget bod mass. Don't forget it. It's so important. Mm. Still getting a little bit hotter. Oh. Ah. I think some. Oh yeah. It just hurts. There are some endorphins. I can feel them. Adrenaline's kicked up. I can feel that. I'm a bit hot. I mean, it's only these little things, but they kind of bite. I'm surprised. Don't bite as hard as a Scotch bonnet, that's for sure. But that's enough. Well, there you go. I think it's reached the ceiling now. Let's not do that again, right? I can't hear anything again. My hearing's just gone. I think it's because I blow my nose. Actually, makes more sense. Okay, it's reached the threshold. It's just there now. It's kind of quite a vicious burn. It's quite quick, but it's vicious. So let's do this again. Um, let's do the multiplication first. So, ooh, I guess this is all pretty much useless. Um, yeah, yeah. Okay. So first of all, we must do um, one sec. Yeah, this is all wrong. Let's clear this out. So it's actually ah, 2 6 minus 1 multiplied by um, 1. So it's 0.6, 0.8 in a product of, well, yeah, okay. Let's just do 8. Then it's 1 II. So let's do 1 II first. 1 II is equal to, oh man, ah, 0.6 times 2. Ah, I think I've done this one already. Just looking over. No, I haven't. Bugger. Okay. Ooh, 0.6 times. Okay, it's gone. It's peppery now. It just tastes like I've eaten green pepper. No, uh, cracked green peppercorn. That's what I meant. It's very, very peppery, and not in the red chili red pepper kind of sense, but more of the condiment pepper. So let me sorry, I forgot to. It's all going pear shaped now. Let me just put this back. Close that. Pull that back down, like so. There we go. Whew, okay, right. So let's get the inner product of 1 and II. So 0.6 times 2. II is the second one. 1 is this one we. This is the second one, and then 1. No, 0.62 is this one, the original one over here, right? So here, um, so it's 0.6 is coming from this one up here, yeah, times 2, and then it's going to be plus negative 6 times 0.8, and that equals, 1 second. Okay, um, so 0.6 times 2 is 1.2. No, it's 0.6 times 2 is 1.2 plus um, negative 6 times 0.8, I don't know. Negative 6 times 0.8, negative 4.8. So it's minus 4.8. 1.2 minus 4.8 is equal to negative 3.6. Negative 3.6. Okay, so we've got our inner product, and we need to scale it by our 1. So um, 1 multiplied by negative 3.6 is equal to um, not, 0.6 times negative 3.6, and then 0.8 times negative 3.6. Let's try that. 0.6 times negative 3.6 is negative 3. Okay, and then this one will be 0.8 times negative 3.6 equals negative 2.8. It's crashed again, sorry. Let's put a report. This is not good. Help. No, about. Oh, there's nowhere to report a bug. Yeah, that sounds about right. Oh well. I won't know. That should be up front and center, shouldn't it? I can't believe you can't do that. Negative 2.8. So let me just make sure this is a bit clearer. I'm doing the inner product was negative 3.6. Now we're multiplying that inner product by this, which means we end up doing negative 3.6 times 0.6, and then negative 3.6 times 0.8, which equals that, and then we've got 2 is equal to 2 negative 6 take away negative 3 negative 22.8. Let's try that. 2 take away 3 is negative 1. Negative 6 take away 2.8 is something positive. Negative 6 take away negative 2.8, negative 3.2. Okay. And then we now we have this. We should be able to draw this, and it makes a bit more sense, right? So if we just change this over, it's going to be um, it says rescale the first by its own length. So you got the two basic vectors are 4, -3, and what's the other one? So 3, 4. Sorry, 3, 4, and then 2, 2, -6. Oh, they weren't orthogonal to begin with. Whoops. Um, I should have really done. Yeah, I suppose it doesn't really matter, but they weren't orthogonal to begin with. But I think we've gone through the process now, and we can finally see that uh, we've done the scaling. We end up with a we scale the left piece by its own length. We now have the second basis vector. It is orthogonal to the first and of unit length. Simple example tells the whole story behind this procedure, which we'll now be discussing general terms in Dirac notation. And you can see it like if we now started to go back to the actual original question, um, of this one, we don't have to imagine these things anymore, right? We can just use algebraic formulation. So let's do that. Let me go in a bit. Whew, that last chili, man, that sent me flying. So we got to the point where we got our next vector, that's fine, and we could go and prove that it would equal 0, but they're not orthogonal in the first place, so it won't equal 0. So it's a bit of a bit pointless. But we've done the process, so we get the process now. And actually, we could have done that dot product, inner product, to find out that it wasn't indeed orthogonal. Um, the cool thing is that we should be able to just do it with these equations now. So if I wanted to do it, if I try to remember it, it would be first we want to do, we're going to get a new one, because, well, we'll say we're going to get a prime, which is going to equal a over the magnitude of a, where the magnitude of a is equal to the square root of the inner product of a. Given that, we can say that b prime is equal to b minus the a prime, the projection, multiplied by the inner product of a prime with, I can't remember, b. Ah, damn it, I did know that. B. Like this. So it's b minus a prime times b. Yeah, the inner product of that. Now we get b2, b prime, and to check that they are orthogonal, we can do a prime b prime is equal to, so this is, we could just calculate that, but it's actually, just to be obvious, it's A prime B prime take away the original the inner product, the unit vector, the inner product of the thing, so the inner product of A prime multiplied or scaled by A prime B, which should equal 0. And now it says, so form an orthogonal basis. We've done that. That's B prime. And then it says, can you generate another orthogonal basis? Yeah, we can, because we can say C prime is equal to C minus C minus well, it says here we go. Yeah, so it's C minus, it's the first one, so it's A prime multiplied by the inner product of A prime and C minus B prime multiply the inner product of B C. And if we want to do another one, D, well, let's just show that. So B C would equal B prime C prime minus B prime B prime B prime C. And we could go on and so forth. So can you generate another orthonormal basis starting with these two vectors? If so, produce another. Let's see if I can type here. Seems to be lagging. I've gotten to the end of the exercise 1.3.1. I want to confirm that I've done this right. Please note that all letters are vectors. A equals 3i plus 4. Actually, let's just grab this up here. Oh no, I can't be bothered. 3i plus 4j. B equals 2i minus 6j. A prime equals A divided by the magnitude of A, where the magnitude of A was equal to the square root of the inner product of A. b prime is equal to b minus a prime times a, the inner product of a prime with b. So therefore a prime with b prime, our new basis vectors, equals a prime times b prime minus b prime multiplied or scaled by the proportion of that. No, sorry, I'm being an idiot. Minus a prime times b prime minus, I guess it's actually the inner product, isn't it? It's actually the inner product. So let's not confuse things. Let's just do that. And I think I've done the same. No, that's fine. Yep. Let's just do that, and then it's minus a, the inner product of a prime with a prime. And then a prime b equals 0. And to generate another orthonormal basis starting with these two vectors, it would be c equals c minus a prime times a prime b minus, if I got that right, it's a, oh, okay, c, fine, minus b prime c b, and therefore b c b prime oh, it says my stream is finished. I'm confused. Hang on. This can't be right. I should be streaming still. I am still streaming. How strange. Sorry about that. Must have been looking at the wrong thing. Let me just go back to my stream. YouTube Studio. This is very strange. I've not had that before. Live. I'm currently live here. Analytics. Well, how do I get back to it? I don't even know. No idea. I think something went a bit strange. Viewing control live panel. I see. Okay. Sorry about that. Yeah. So therefore, BC would equal oh gosh, it would equal, if we go back to this one up here, then it's the primes minus the original primes scaled by the original. Let's see. So it's the B C minus, no, is it scaled or minus? It is minus, okay. BC B prime scaled by B prime C. And we could, does this all look right so far? Let's see. Whew. I've only just gotten over that chili, by the way. So it says, your general procedure seems correct, but let's break down the steps to ensure clarity. Normalize vector A to obtain A prime. Yep. Where A, the magnitude is the magnitude of A and is computed as the square root of A dotted with itself. Yep. Dotted with itself. Okay. Subtract the projection of B onto A prime. From B to orthogonalize B with respect to A prime. B prime equals B minus A prime dotted with B scaled by A prime. This ensures that B is orthogonal to A. To check the orthogonality, A prime equals A dotted with B. If this equals 0, so that's interesting. So A dotted with B minus, okay, if there's a third vector C, which isn't mentioned in your initial but is in your steps, to make it orthogonal to both A and C, C equals C minus AC minus BC B. This will ensure that C is orthogonal to A. To check the orthogonality of B and C, if this equals 0, then B and C are orthogonal. However, I noticed in your explanation, BC, this doesn't quite make sense in the context of orthogonality checks. The idea is to take the dot product but directly determine if the vectors are orthogonal. Which is essentially correct, but the notations and steps in the last part related to C are a bit off. Ensure that you're following the steps correctly and check each step for clarity and consistency. So let's go back to this one. B we want to check the dot product of B and C, which is check the dot product of B and C, which is A and B, so it's the same thing, B and C, minus dot product of B multiplied by B and the one that we want. Oh, therefore, I see, therefore equals 0. There you go, that's what I did wrong there. I'm actually really tired from that chili. Goodness me. I haven't done that for a very long time. It's actually quite a lot of craziness going on there. Probably not the best idea to try and do to punish your maths because I just like went into a trance. So in this case, it says normalize A, project B onto A, and subtract this projection from B. So this is the projection. This step also seems to be in line with what you've written. After these steps, A and B should be orthogonal, and both are normals. Now, if you're given a third vector and you want it to be orthogonal to both A and B, you'd extend the Gram-Schmidt process. Project C onto A, so AC, project C onto B, subtract these projections from C. Again, after this, A, B, and C should all be mutually orthogonal. However, there seems to be a mistake or typo in the equation you provided for C. The expression C equals C minus... Oh, did I not put C prime? Yeah, it should be C prime, sorry. C prime equals C minus A prime. Um, and then it should be so the projection of A onto C minus the projection of B onto C. Save and submit. Let's try that one. A prime, where this gives a unit vector, which is correct. Projection of B onto A and correction. B prime is equal to B minus A. This corrects B by subtracting out the component that lies along A. This step seems correctly outlined by you. Ensuring orthogonality. If you want to check that A prime and B prime are orthogonal, you can compute their dot product. The step where you provided 0 is redundant and a little confusing. Once you've... Oh, but this is in AB, A. It's actually... So this is wrong. It's actually AB. AB minus A prime, A prime, A prime B. And this one will be C prime is equal to C, take away the projection of A onto C, take away the projection of B onto C, and therefore the dot product between these two are going to be the dot product between these two minus, so this is wrong, it should be it should be it should be B, dot product of B onto C prime minus dot product of B prime multiplied by B prime inner product of C. Let's try that. You're normalizing A to make it a unit vector. This is correct, where A is equal to that. B, you're then orthogonalizing B with respect to A and then normalizing it. B minus A times that divided by B minus A. B prime is equal to B minus A times that, yep, divided by B minus minus the magnitude. It's important to ensure that B is normalized after the orthogonalization. Your equation, this isn't quite right. What you should be seeing is AB equals 0. AB equals minus A equals 0. What you should be seeing is the dot product of A and B is 0. Which is 2 minus the part point. Think of the arrow. Not surprisingly, it is orthogonal to the latter. So I've got A prime Oh no, I'm losing it again. I'm losing it, I'm losing it, I'm losing it. It's just when you go on for too long, isn't it? Um, don't lose it now, James. Come on, you can do this. You can do this. You must do this, because you're never going to go forward if you don't do it now. So let's do this, man. Where have I gone wrong here? I've got the first basis is equal to this vector over the magnitude. And then it's, so I've called it A prime. As for the second vector in the basis, it's funny because one is, I don't like this syntax. I really don't, because why change it halfway through? Honestly, it's saying that this first one is special because you don't need to have the original one, but like you start with a vector and then you get this prime, this new basis vector. But then it's saying that, and as for the second vector in the basis, let's change the way it's written. It's like so confusing. Um, let's try this again. So, from my head, if I want to get if I want to get a prime, then that's going to equal to a divided by the magnitude of a, where the magnitude of a is equal to, where a is the magnitude of, where the magnitude of a is equal to the square root of the inner product of a. Now, if we want a second basis vector, a prime is a basis vector. Now, if we want a second basis vector, b prime, and we have b to work with, b prime is going to be equal to a, is going to be equal to b minus a prime times by a prime, no, a prime b, because we've got our orthogonal anyway, and then we are so it's going to be the it's going to be the one that we've generated, which is going to be a prime, inner product of the one that we want. Now we have our new basis, b prime. We can check its orthogonal. So b orthogonal to a prime, to the other basis a prime, by doing
a prime b prime is equal to, it's b, it's the inner product, so the inner product of the two must be equal to the inner product of the first one and b minus the projection multiplied by the projection b. And that makes sense because we're saying that AB minus something scaling AB is equal to 0 because A prime equals 0 because it is orthogonal to itself. Hang on, so we got our dot product minus something scaling our dot product. No, because because um, because a b equals 0 because it is orthogonal to its to the original vector, because a prime is orthogonal to the original vector b, and so scaling a prime by 0 you've got the inner product of a and b, a prime and b, prime and b, minus the original inner product times by the inner product of the two. So a prime b equals 0 because does not equal 0. It's just because it's the unit, I see. Because a prime equals 1, because this inner product divided by the magnitude of a to the power of 2 will make it a unit vector 1. It will make it a will equal 1. So clearly, scaling a b by 1 and then negating itself will equal 0. Now, for the second part, it says, can you generate another orthonormal basis starting with these two vectors? I can, because C would equal it's C minus B A prime, the projection of A onto C minus minus, or is it? It's A prime times projection on C, and then B prime times the projection of B onto C. And we can prove this is orthogonal because C, the inner product of because B C equals, let's just do AC first, is equal to the A prime um, this should be C prime, and equals to, so it's it's the original vector, no, the original basis, inner product of the original basis with C is equal to the inner product of the original basis minus A A A C, which equals 0, and B prime C prime is equal to B prime C prime minus B B B C, because we already know A prime equals 1, and so does B follow this same strategy. And we could then therefore do the same with another one. D prime is equal to D minus um, D minus the projection of A prime onto D minus it's this A prime D, and then minus C prime multiplied by C prime onto D minus B, well, I should do B first. B, and then C prime onto D. And we can prove that is orthogonal in much the same way. Is this all correct? See if I did something wrong. So A prime is a normalization of A, where A is the magnitude of A. This step looks good. To get B prime, which is orthogonal to A prime, and then normalized, B minus A prime times A prime B divided by the magnitude. The formula you provide appears correct for the orthogonalization of B with respect to A. Your proof of the orthogonality uh, of A and B is correct indeed. A, B equals 0 because the way B was constructed. For C, if C is some third vector, yes, this equation is correct, and it's the Gram-Schmidt procedure generalized for a third vector, the formula of proof. And yes, the same procedure can be repeated by D, provided they aren't already in the span of A, B, and C. Each time you introduce a new vector, you subtract out its components in the direction of the previously established orthonormal basis vectors. Your understanding seems correct. Just ensure you're careful with your calculations at each step to maintain your orthogonality and normalization of your resulting vectors. If you want to establish an orthonormal basis using the vectors provided, you'll need to be sure you start with vectors that aren't linear combinations of the previous ones. So we've done it. I think we've done it. So let's. I think what we should do now is plug in some numbers to that. So I'm going to go to a new sheet because this is just way too laggy now. Um, and this I need to rework because I need to make sure that orthogonal to begin with. Just to be clear, is it that vectors A and B would have had to have been orthogonal with each other for this to work? No, okay, that's good. So I did understand that. So now if we go back to this, um, that's the yeah, it's actually the whole point of it. So we go back to this, we had um, two, but we could have actually figured this out. Like if they end up being zero, then we've done it right. Was it this one? Was it this one? P minus P. Um, yeah, and then we did 0.6. Then we did that. Yeah. So in this case, if I go back here, my little screen, we could have said, let's just see. We go, is is 1 orthogonal to 2 prime? And the answer will be 1, 2 prime minus minus the inner product of 1 with 1 and then 1, 2 equals 0. And we can prove that because the inner product of 1 with 1 is inner product of 1 with 1. So 3, 4. It's 3, 4, and then over the inner product of 3, 4, which is which is 3 times 3 plus 4 times 4. And where did I do this before? 2 times 2 plus 4 is 25. And so 25, if I just go back over here again, uh, it's the inner product. So it's 25 divided by 25 divided by 5 squared equals 1. So this equals 1, and so this will equal 0, and so we do have an orthogonal vector here. So we've proven that. Well, that's a bit good, isn't it? I suppose it's kind of strange because, so geometrically speaking, with 2D vectors, am I right in thinking that we couldn't just draw this onto an axis with x and y? Because if you plot the vectors, they wouldn't all be orthogonal to each other. It's impossible. But that's the point of this being a quirky quantum mechanics thing. Because I think I plotted it here, didn't I? So I said um, maybe I didn't actually, 2, 6, 3, 4, and then we've got minus 1 minus 3.2. As you can very much draw this onto a 2D plane with x and y, and it works perfectly without any quantum quirkiness. The idea of orthogonal vectors isn't limited to quantum. It's a fundamental concept, and if they are linearly independent, not pointing in the same or opposite direction, they will form a basis for the plane. This means any point in the plane can be reached using a linear combination of these two vectors. If the two vectors aren't orthogonal, they don't form a 90 degrees angle between them, then the Gram-Schmidt process can be used to produce two new vectors that are orthogonal to each other. For instance, consider your vectors 3, 4, 2, 6. These vectors aren't orthogonal to each other if you plot them on the xy. Agreed. Let's just go and do that. So 3, 4, and 2, 6. Let's just take away for these for a second. However, through the Gram you produce new vectors a and b prime that are orthogonal to each other. If you plotted a and b, they would be perpendicular. Ah, I see. So it's 0.6. So let's do that. 0.6, 0.8, and then -1, -3.2. So I must have gone wrong somewhere. But this isn't quantum mechanics thing, but a plain general. Okay, so um, with A and B being what you've stated, 1 equals 3, 4 divided by square root of 25 equals 0.6, 0.8. And then 2 would equal 2 -6, take away 0.6, 0.8 times the inner product of those two. So the inner product of those two is, and then 1b is equal to 0.6 times 0.2 0.6 times 2, sorry, plus -6 times 0.8 equals 1.2 take away 4.8, which equals -3.6 times -3.6, which equals um, negative. So 0.6 times 3.6 negative. Okay, equals um, equals times 1b. Therefore, 2 equals 2 -6 take away -1 -3.2 which equals 2 take away -1. 2 take away -1 is 1, right? So 2 take away -1 is equal 3. Ah, here we go. So 2 take away minus. Now hang on. So we got this multiplication equals it ends up being 2 take away. Ah, it's frozen. 2 take away 3 -2.8. So 0.6 times 1b would be 0.6 times -3.6. Then it's 2.6, it's -3. So 0.6 times -3, 0.6 times -3 equals -1.8. Where am I going wrong here? Oh, -3, why did I do that? 0.6 times -3.6, -2. Oh, okay. I think we're actually there, almost. I just need to figure out in my head where we're going with this. So, and then 1b equals this, because it's 0 0.6 times 2 plus negative 6 times 0 0.8 is 1.2 take over 6. And so therefore, it's 2, 6 minus these two multiplied together. So 0.6 times 0.6 times negative 3.6 0.6 times negative 3.6 equals negative 2.16. So take away 3.6 is negative 2.16. 6 up here. And then, this is, because we've got the inner product, we need to multiply these together still. So I think this is probably wrong. Um, yeah. So it's actually 0.6 times negative 3.6, and then 0.8 times negative 3.6, which equals negative 2.6, and then 0.8 times negative 3.6 equals negative 2.88. Let's just make sure. So 0.6, the inner product is 1, which is that. So it's 0.6 times 2. So this is 0.6 times 2 plus negative 6 times 0.8 equals 1.2, and because negative 6 times 0.8 is a negative, then it's not negative, so we end up with that. So now we're multiplying um, this with this. So we got 0.6 times negative 3.6, which is that. 0.8 times negative 3.6, which is that. Um, this whole thing, which is 2 take away negative 2.6, and yeah, okay, cool. And so then this would equal 2 times negative 2.6. This is 2 times negative 2.6. 2 times negative 2.6 is negative 5.2. Aha. Negative 5.2. And then negative. No, no. We're not trying to do that. We're doing 2 take away negative 2.6. 2 take away negative 2.6 is 4.6. Because we've already multiplied this together, we've already got that, so we're just taking away now. And then negative 6 take away negative 2.88 is negative 3, 1, 2. And so now it's going to be the inner product of 1, 1 is it's the inner product of 1 and 2 is so this is the answer here. That's 2 prime. And so it'll be 0.6 times 4.6 plus plus 0.8 times negative 3.12, and that's this, equals, let's just do that, 0.6 plus 0.6 times 4.6 plus 0.8 times negative 3.12 is 0.264, and then this will equal 1. And so now we've got take away 0.264 equals 0. So let's now plot these ones in. It's going to be 4.6 negative 3.12 should be orthogonal to 0.6, 0.8, and it is. Ah, that's awesome. Yeah, okay, cool. So 2 is 2 is um so 1b is negative 3.6, and so 2 is equal to 2 take away 6, and it's negative 2.6, negative 2.88, negative 2.88, which equals 4.6 take away 3.12. Therefore, what is this? What's this telling me? I am going a little bit high, but I'm only 0.9.2. Let me just finish this off then. Therefore, the inner product of 1, 2 prime will be equal to 0.264 take away 0.264, which equals to 0. And indeed, if you plot 1 with 2 prime, they are indeed orthogonal on a 2-dimensional plane. Yeah. I think that's a proper reward now. That's not a negation. I'm just going to go and get my injection 1 second. You've got the gist of it. By using the Gram-Schmidt process, you've created 2 orthogonal vectors from the given vectors A and B. As a quick correction, to compute 2, you used the formula 2 minus, but you didn't show how you got the numbers. I think what you meant was that you were scaling 1 by 1b. Equals negative 3.6. Negative 3.6 times 6, yep, 2.8, so 4, 3, yep, got it. thus the two vectors 1 and 2 are indeed orthogonal on the dot product. If you plot 1 and 2 in the 2D plane, they would be perpendicular to each other. Great work. This approach to generating orthogonal vectors is fundamental in many areas of science and engineering. We get to avoid those bad boys. Let me just put these back in the fridge. And let me just do my ejection, then we'll just do a little summary, I think, because that's a good place to stop, because I'm actually on to the next part now. We'll have a little look at it, but finally off of this bloody page. Haha! Yoo-hoo! Progress! Okay, so, to summarize, we have figured out that, I'm doing this because I want to see if I've got it in my head. We figured out that 1, if you have a vector, let's call it I, then you can create a basis out of it by doing the vector I divided by the normal of that vector. And that's where the normal of that vector, is equal to the square root of the inner product of that vector. Now, we can make another vector, we'll call this 2 prime, another basis by saying that we take we take our second vector, which is going to be II in this case, and we take it away from the first vector scaling the projection of 1 onto 2, or 1 onto II. Now, we know this is orthogonal with 1 because the inner product of I and I is equal to the inner product of I divided by the magnitude of I squared. And if you look up at this, you can see that the square root of the inner product squared will be equal to 1. And so, given this case, we can now say that 1 and 2 prime are orthogonal because if you were to take 1, 2 prime off of the scale of one of 1, 2, this is some other vector, but this is 1. And so these will equal 0. And then we can make any more. We can say, okay, 3 will be equal to 3 i's minus the first projection scaled by the projection of this onto I, take away 2 prime scaled by 2 with a projection of that, and so on and so forth. And let's go back to our Kindle. Let's just make sure we got this right. 3 is 3, take away 1. 1, 3, minus 2, 2, 3. Oh, yes. That is amazing. 2 hours, 50 minutes. We're there. Let's leave this page. It says show how to go from the basis 1, 2, and 3 to the orthonormal basis. So, um, we could say in this case, if we go along one again, over here, let me just do this. Okay. We can do that by so how to go from the basis I, 2, and 3 to the orthonormal basis is you would divide that by the norm. And so I equals 3, 0, 0. You just want to divide that by show how to go from the basis to the orthonormal, go from the basis to the orthonormal basis. I think it says it here, doesn't it? It says we now divide 2 by its norm to get 2, which will be orthogonal to the first. We now divide 2 by the original. So if we took its I is going to be 1 is equal to well, it's got numbers, so let's just do it. 1 is equal to 1 is equal to I take away no divided by the norm of I, and the norm of I is equal to the square root of the inner product of I, and so it'll be the inner product of I will be equal to 3 times 3 plus 0 times 0 plus 0 times 0 equals to 3. And so 1 is equal to 3 divided by, well, you can imagine 3, 0, 0 divided by 3, 0, 0 will give us 1. Now, let's just try it for the second one, because then you've got 2 prime, or 2, I guess, is equal to um, is equal to II minus II minus 1 scaled by the inner product of 1 on II. And so II is 0, 1, 2. And so the inner product of that is going to be, so let's do this one, is 3 times 0 plus 0 times 1 plus 0 times 2, which is equal to 3, 0, 0, and then we've got this part, which is 3 times, no, hang on, this is not equal to that, it's equal to 3, 3 times 0 plus 0 times 1 plus 0 times 2 is 0, and so 3 uh, 3 times, so anything times 0 is 0, right? So it's going to be 0. And so 2 is equal to um, naught naught take away 0, 1 take away, what did they say? 1 divided by the square root of 5. Um, so now we've got 2, and we've done this equals 0, and so does it equal 0? 1 is 1 is 1, 0, 0, and so 2, they've said 2 to the north, 2 is 1 over square root of 5, but I'm not seeing that at the moment, so that's because one with I is not this. One is 1 times, here we go. So it's 1 times 0 plus 0 times 1 plus 0 times 2, which equals 0. And then for this part, it's 1 times 0, 0 times 0, 0 times 0, which equals 0. And therefore, it's just I, so it's going to be 0, 1, 2. But they're saying it's 1 over the square root of 5. So what's the square root of 5? It's equal to 5. 1 divided by 5 is... Wait, square root of 5 is 2.23. So 1 divided by 0.44 0.47, and then 2 divided by 2 divided by equals 0.89. Um, Show how to go from the basis to the orthonormal basis. Oh, okay. Interesting. When we first learn about dimensionality, we associate it with the number of perpendicular directions. In this chapter, we defined in terms of the maximum number of linearly independent vectors. The following theorem connects the two definitions. Theorem 4. The dimensionality of a space equals n to the inverse transpose, the maximum number of mutually orthogonal vectors in it. To show this, first note that any mutually orthogonal... So this exercise 1.3.2 is not explained. So we found out how the I goes to the 1. We did that. But then 2 goes to... that because it's II minus 1 times 1 over 2. 1 product of 2. And the problem is, if we do that, is that II is 0, 1, 2, but 1 is 1, 0, 0. Let's see what GPT-4 says, because I'm a little bit confused here, I have to say. So when on exercise 1.3.2, it says to show how to go from the basis I equals 3, 0, 0, 3, II, 0, 1, 2, and then III, 0, 2, 5, to the orthonormal basis. 1, 0, 0, 2, square root of 5, square root of 5, and then 5, square root of 5, negative 2, 1, 0. I can do the first one because I, no, 1 is equal to I divided by magnitude of I, which in this case will equal, which magnitude of I, where I equals the square root of inner product of I. And so so I equals 3.3, 3 times 3 plus 0 times 0 plus 0 times 0, which equals 9. 9. Um, so yeah, this is wrong. This is wrong. Oh man, I guess I'll go and get the chili because that is just that's just wrong. It's 9. 3 times 3 is 9. Oh my god, this is ridiculous. Clearly it's not working. I'd be absolutely sure here that I've done this wrong. Here's my chili, but bear with me. I definitely did this wrong because the inner product is 3 times 3 plus the zeros plus the zeros. So I had the 9. Yeah. Let's get the extreme close-up camera here. This is ridiculous. I cannot believe I've done this again. Um, so the first one was I didn't keep the negation of 6. The second chili was I had I'd forgotten BODMAS. So this one is I I just didn't follow what was on the page. Oh man, wish me luck. You know, I don't have to do this, by the way. Fuck. This tastes nicer, at least. Hmm, it's actually quite nice. Yeah, it's actually quite nice, that one. Is it hot? No, it's not hot. I mean, it's hot, but it's not. That wasn't a punishment. That one. That was very nice chili, though. Cool. Okay. Well, um, it's a pretty serious error, so it's surprising that I got that wrong. It's not really that surprising. Anyway, let's continue. So, um, yeah, that wasn't shocking. Oh, it's lovely though. Really lovely taste. Okay, so if this is 9, then it's 3 divided by the magnitude. It's going to be um, it's the square root of 9, which is 3, and so then we've got, yeah, this. I think I must have projected forward, right? Um, let's do that. Let's do that. And then you've got uh, 3 divided by 3, and that equals 1. 3 divided by 3, yeah, that equals 1. Okay, cool, good. So it wasn't, well, at least we haven't gone too far wrong. And so she equals 9, and so square root of, which equals 9, which equals square root of 9 equals 3. And so um, the vector divided by 3 will equate to 1 to the basis that the book states. Now, moving on to 2, so maybe we just did a silly billy mistake, and that's quite possible, but I guess what we could do is just do the whole lot again and again. That's exactly what it's doing. Yes, I understand it now. I understand it. We're not trying to do that. We're trying to prove that they are. Oh, things bloody gone wrong again. Oh, we've got it. I've got this so much now. I've got this. This is gonna work. Okay, this is awesome. So if I go, yeah, 0 0 1 2, so I is equal to 0 1 2, then we could just do the same thing, right? We can go 2 is equal to the square root. Well, what's 2 with 2? II with II is equal to 0 times 0 plus 1 times 1 plus 2 times 2, which equals 0 plus 1 plus 4, which is equal to 5 square root equals, yeah, that's fine. So then you've got 2 is equal to uh, 0, 1, 2 over the square root of 5. Um, let's see, 1 over the square root of 5, 1 divided by the square root of 5, and 2 divided by the square root of 5. Yeah, cool. And then the third one, we'll just go over here. Easy, so we got it. We got that one. That was easy. So, 3, sorry, I is equal to the, what's this? I is equal to 0 to 5. And so this will be 0 times 0 plus 2 times 2 plus 5 times 5, which is equal to 4 plus 25, which is equal to 29. Square root of 29, what's that? I may have done this wrong. 29 square root 5.3, so I probably did something wrong. Let me just check. 0, 2, and 5. Ah, it says here, just double check that it's the III is equal to that, and it's also equal to -2 over the square root of 5. Interesting. So let's approach this a little differently. Well, actually, did I just do that right? It'd be 0 to 5. 2 times 2 plus 5 times 5. 2 times 2 plus 5 times 5. I quite like this actually, just doing that. But it's actually equal to the square root of that. And so No, it's not. It's not. That's not how this works. No, no, no. Um, it's actually it's 2 times 2 is 4 plus 5 times 5 is 25. It is square root of 29. So if I do the square root of 29, it's 5.385. And if I do um, negative 2 divided by the square root of 5, negative 2 divided by the square root of 5, 2.36. Negative 2 divided by the square root of 5 is equal negative 0.89. So let's just capture that. Whoa, that was massive. Try zoom back up again. Don't know why it did that. Very strange. And then let's try the other one, which is 29 square root of 0.25 to the orthonormal basis. Oh, that is interesting. The vector divided by 3, which makes equal. Now moving on to 2. This is the exact same problem. Let me just go back and describe this because I might need to put this in. Because 2 equals II divided by II magnitude II equals 0 times 0 plus 1 times 1 plus 2 times 2, which is equal to 5. We'll do that. Of 5. And so yes, 2 equals 0, this. The third one is a little more tricky. I think I did 3, but I meant to put, yeah, it was this. Because if I apply the following rules, II equals equals 0 times 0 plus 2 times 2 plus 5 times 5, which equals 4 plus 25, which equals and that does not seem to equal the expected output. Let's see where I've gone wrong. Sorry, I've put my Facebook up here again. I totally forgot all that time wasted. Sorry about that. I won't do that again. I'll make sure I won't do that again. I see where your confusion arises. Let's take this step by step. By given the original vector space, you correctly found the first normalized basis. For the second basis, you correctly found this. Now for the third basis, we don't just normalize I. Oh, before it goes on then, let's just try this, because I think I know where it's going to go. And I think I also was maybe not sharing this for the correct amount, but we could do we could do 3 equals 3 equals I minus I at 1 times 1 I minus 2 I, and then this would equal this here. Ah, yeah, that's fine. Let's do that. So this will be 1 times, it'll be uh, it'll be 0, 0, 0 actually, because it's actually it's 1, so it's 1 times 0, and then it's 0 times those, so you get zeros. But this one, slightly different. It should be that. Will be 1 over 1 over 1 over, let's just do it. So it's 2 is 0 times 0, 1 over square root of 5 times 2, and then 2 over the square root of 5 times 5. And then we're multiplying that. There's going to be 1 over the square root of 5 multiplied by that, 2 over the square root of 5 multiplied by that, and it's actually these are plus each other, aren't they? So let's do that. So 1 divided by the square root of 5 times 2 bod mass. Yeah, that's wrong. So it's 1 divided by the square root of 5, and then times that by 2, and then times that by 1 divided by the square root of 5 equals 0.4. Um, so it's 0 plus, let me just do this again. 1 divided by the square root of 5 times 2 equals 0.89, and then let's put that in memory. 2 divided by the square root of 5 times 5 equals 4.47, and then plus memory recall equals 5.366. Um, so if I want to add fractions together, do I just add the top and the bottom? So 1 over square root of 5 times 2 plus 2 over square root 2 over square root of 5 would be 3 over square root of, no, it wouldn't be. Okay, let's just read what it says, because times 2 and then times 5, so we've done that, and it says 0, 1 over 5 and 2 over is equal to 0, 2, 4. Is it now? Is it now? But we're on the right track, right? So, 1, I swear I did that right. So 1 over the square root of 5 is 2. So so start by projecting 3 onto the other two basis vectors. 1, I did that. 1, 3 times by that, yep, is equal to 0. Yeah, I've got that right. Okay, that's good. That's good, that's good, that's good. And then this one is more tricky because we've got 2 which is in these fractions. So it ends up being 0 times 0 plus 1 over square root of 5 times 2 plus 2 over the square root of 5 times 5. And if I put that in, 1 divided by the square root of 5 times 2 plus 2 plus 2 divided by square root of 5 times 5 equals 0.8, 0.89, but this is saying, so maybe we can just work without calculating them, which would be interesting. Because 2, yeah, so how do you, it's kind of going slow. How do you add fractions like, how do you multiply fractions like this? 1 1 over square root of 5 times 2 plus 2 over square root of 5 times 5 all times 2. You managed to get 0 to 4 from it. But if I do it, 1 divided by the square root of 5 equals 1 divided by the square root of 5 equals 2 times equals and then 2 divided by square root of 5 is equal to, so 2 divided by the square root of 5 equals, and then 5 times that equals this. And now to multiply, no, now to, and now adding them, this plus this equals 5.36. And now I multiply 0 times that, um, times this equals 2.4. And um, and then 2 over fifths. Oh, it should be that, shouldn't it? 1 over square root of 2. No, that's right, yeah. So it's that one times maybe it should be that though. Not adding them equals that, yeah, so it's that times that. Equals 0, 2.4, 4.8. Where have I gone wrong? Given 2 is equal to that, yep, and 3 is equal to that, oh, my neck's hurting now. I've been on the seat way too long today. Let's lock this chair off for a second. Start by calculating the inner product. 2, 3. So 2, 3 is 0 times 0, 1/5 times 2, 0 plus 2, 1/5, 10, 2/5. First, let's calculate equals 0.894, which I got. Yep. Next, 8.94, so 10 times. Um, but that's a good point though, because I suppose in a way I could have just done that, couldn't I? It's just 2. It's 0 plus 2 1/5 or 2 1/5, 2 1 like that plus 5 2 over 5. I probably went wrong there, so let's try that again. It's 5 times 2, 5 times 2 divided by the square root of 5 equals 4.47. 2 times 1 over 5. Ah, that's why. 2 times 2 divided by square root of 5, 0.8. It's like I made a mistake in the previous penalties that your accuracy correct. Thank you for pointing that out. No, I don't think they do. I don't think they do. Let's just get this really clear again. So, because I make lots of mistakes here. So, this looks correct. So, it's just this side that I really care about. I want to do 2 times 0 plus 2 times 1 over square root of 5 plus 5 times 2 over the square root of 5. And if I calculate those, I've just literally done that. 2 times 1 divided by the square root of 5 equals, so 2 1 over square root of 5 is equal to 0.894, and then 5 times 2 over square root of 5 is equal to 5 times 2 divided by square root of 5 equals 2. That's not right. 5 times 2 divided by the square root of 5, 4.47. I don't think this is what they expect me to be doing here. Because why? What's the point, right? So let's just put that over there. Um, so let's just keep it like that, and then it's going to be, it's 2 times 1 over 5. Let's see, equation. How to multiply square roots. How to add fractions. How to multiply square roots without actually calculating it. Because how do you add fractions together? How does fraction? It's 1 plus 3 over 5. Um, Identify whether the denominators are the same or different. In this case, the denominators are different. If they are the same, move on to step 3. If they are different, find a common denominator. For this example, you cannot skip the second. What's a common... No, they are the same, so you can just add it. So it's... Okay, so it's 5 times 2 is 10 over square root of 5 plus 2 over the square root of 5. Ah, I didn't know this. I did not know this. And so it's going to be equals 12 over the square root of 5. Is 2 0 plus 2 1 over square root of 5 plus 5 2 divided by square root of 5 equal to 2 divided by square root of 5 plus 5 divided by 5 times plus 10 over square root of 5 equals 12 over square root of 5. We can, I guess we can just work it out, right? So, um, so to, let's just do it in Python here. So 2 times 0 plus 2 1 over was it Python for square root math square root plus 5 times 2 print. So you got 2 times 0 is 0, so we don't need that. 2 times 1 over the square root of 5 plus 5 times 2 over the square root of 5. Run. I need one to close. Int object is not callable. Perhaps you missed a comma. 2 times 5 2 5 times run 5136. And if I then do print 12 divided by math.square root of 5, they're exactly the same. Okay, cool. Yes, let's break it down. Cool. Okay. I didn't know that. That might make life a little bit easier, huh? So now we know that, um, we can just multiply this, right? So it's going to be it's 12 over the square root of 5 because of this. I did not know you could do that. That is wonderful. That is really, really helpful. And so now we're going to multiply this, right? So it's it's um it's 0 1 over 5 square root 2 over square root of 5 times 12 over square root of 5. So 0 times that is 0, and then we're going to have 1 times 12, so it's going to be 12 over square root of 5, and then you're going to have 2 times 12 is 12, so it's 24. Um, how do you multiply fractions? Step 1, 3 times 2, 3 times 2 is 6, 4 times 5 is 20. Cool. So it's 24 over square root. So square root of, I can't read this. This isn't helpful at all. 0, no, yeah. 0, 1 over square root of 5, 2 over square root of 5, multiplied by 12 over the square root of 5, is equal to 0 times 12 over square root of 5 equals 0, 1 over square root of 5 times 12 over square root of 5 equals 12 over square root of 5, and then 2 over square root of 5. What's how to multiply square roots together? So then, if I were to do 2 divided by square root of 5 times 12 divided by square root of 5, 2 divided by square root of 5, 2 divided by the square root of 5 times 12 divided by the square root of 5, that's what I wanted, is the same as, let's see if that's running, 2 divided by the square root of 5 times 12 divided by the square root of 5, print, which should be equal to 2 times 12 is 24. 2 times 2, 24 times the square root of 5. 24 divided by 2 times 12. No, I see. Square root of 5 times it's 25. Cool, okay, good. Good. Equals 24 over the square root of 25. This one here is what we've got now. Or maybe I'll just do it in a better colour. And so this is our 3. Um, uh, Almost actually, because we have to do 0 to 5, take away 1 times 0, so it's going to be 0, because we're doing 1 times 0, 0, 0 times 0, 0 times 0, take away, um, take away 0, 12, um, divided by square root of 5, and 24 divided by square root of 25 equals let's see what we got here. So 2 12 over the square root of 5 2 take away is that, and also um, minus 2 square root over 5 minus 2 over square root of 5. They're not the same. 2 take away square root of 5. No. I've gone wrong somewhere again. Ah, this is so annoying. It's a bit difficult, isn't it, to not make a mistake somewhere. So we have III 0, 2, 5. 0 times 0 plus 2 times 2 plus 5 times 5 is 4 plus 25. Now we're doing the square root of 29. So that's the inner product. And we found out that that's no good to us. So in the end, we thought, okay, well, let's just work out the third basis. So we did III, which is 0 to 5, take away 1. 1 is 1, 0, 0. So 1, 0, 0. If we multiply that, it's going to be 0, 0, 0. So that whole thing is 0, 0, 0 multiplied by 1. It doesn't matter, it's all 0, 0. So it's completely taken away. So take away 0. And then we end up with this last one, which is a bit more complex. And we did these equations. So let's see what it says at the end of this. Now subtract. So it says we've got 0, 2, 4. Now where did perhaps it go wrong? Because it thinks that equals 0, 2, 4. Yeah. Um, let's get rid of this. I wonder where I've gone wrong. It must be these things. We're taken away, but that's so it's still 2 times this. So 2 is this 1 over 5, 1 over square root of 5, and we did adding these together. We did 2 0 times, so 0 is the top one. And then we did 1 over 5 times 12 over square root of 5. And square 12 because 2, 0, this was equal to the same thing, wasn't it? So 1 over square root of 5 times 1 over square root of 5 times, it can't equal this. It's 25. It's 12 over 25. So that's going to equal the same then, 12 over 25. So then it's 12 over the square root of 25, and then square root of 25 now it's 2 minus 12 over the square root of 25, and then if we did 1 divided by the square root of 5 times 12 divided by the square root of 5, 1 divided by square root of 5 times 12 divided by the square root of 5 times 12 divided by the square root of 5 is equal to 2.4. And now if we do 1 times 12 is 12 divided by the square root of 25, they're equal. So I have done that right. Now, and then it's 2 times 12 and then it's 25. So then we've got 0, 12 over 25 and 24 over 25. Um, and then they say now subtract the projections from 3. I. So I equals okay, no, I've already done that. And 12, so 12, 2 take away um hmm. So if I go back to this, so if I do 3 equals I minus 1 1 I minus 2 2 I let's just make sure it's a bit easier to read. So it's I minus 1 2 I minus 2 2 I end up with um with 1 oh it's 1 sorry, equal to 0, and then 2 equals 0 times 12 over square root of 5 equals 0, 1 over square root of 5 times and 2 equals oh, hang on, I've done a boo-boo here. Let's just start this again for a sec. I think I've done a boo-boo. I think I've done a boo-boo because it's 2 is naught naught, okay. Then it's going to be 1 over square root of 5 times, this is it, this is where I went wrong. Yeah, negative 2 over square root of 5. That's it. We figured it out. 1 over square root of 5 times negative 2 over square root of 5. Uh, that was probably the problem. So 1 times negative 2 is negative 2 over square root of 25. Negative 2 times 1, and then 2 over square root of 5 times 1 over square root of 5 equals 2 times 1 is 2 over 25. And so if I multiply that then, well, if I add that together, sorry, plus plus, I equal minus 2 plus 2 is 0 divided by the square root of 25. 0 divided by square root of 25 is equal to 0. And so it's, and now it'll be 0 minus 0. 0, 2, 5. Must have gone wrong here. Um, that's definitely right. Minus the 2. 1 times this. 1 times this is going to be 1 times 1 times 0, 0. And then it's going to be 0 times that, 0 times that. Uh, no, it's not. It's going. Yes, it is. So then you plus zeros together, you get 0, and then 1 would be 1 times 0 plus 0 times so plus 0 plus 0. You're going to have 0, and then that's going to be 1. So it's minus 0. And the second one is 0 times 0 plus 1 over 5 times negative 2 over 5, and then it's minus 2 take away 2 is minus 4. Um, minus 2 over 25 take away minus minus 2 divided by 25 plus 2 over 25 is equals to 0. Minus 2 plus 2. No, I didn't mean to do that. Is that plus? Yeah, it's plus. Is that plus? Yeah. Um, that equals 0. So if that equals 0, then the whole thing, 3 minus 0, is just 0, 2, 5. And so 0, 2, 5. And so she had to go from the basis to the orthonormal basis. So if I do this, I end up with equals 0. And then 2, 3 is equal to 0 times 0 1 over square root of 5 times negative 2 over the square root of 5 equals negative 2 over the square root of 25, right? And then 2 over square root of 5 times 1 over square root 5 equals 2 over square root of 25 um, equals -4 equals 0 plus -4 oh it equals 0. Is that right so far? Hmm. So for the term, given that, for the term 1003025, the inner product of that is 0. Thus, equals 0. You're correctly calculated that part. For the term 2, given 1 over fifth, 2 over 2 fifths, the inner product is expanding 0 times 0, 1 over fifth times 2. Why is it times 2? Oh, I see. Yeah, yeah, okay. Fine, it's the original part. Okay. Um, let's see. That's times 2 times 5, 5 over 2 over 5 equals 12 times. Aha, okay, cool. That's good. That's good. That's good. So we can correct that a bit. Wow, this is lots of mistakes I make. Very bad. So 0 times 0 equals 0. Um, 1 fifth times 2. 1 fifth, 1 fifth times 2 equals 2. Okay. 2 over square root of 5. And this is equal to 5. 10 over square root of 5, which equals 12 equals 12 over square root of 5. So if I do 2 times the square root of 5, 2 divided by the square root of 5 plus 10 over the square root of 5, 1 times 5. Ah, because you have to do like that. So 1 times 5 is 10 over the square root of 5, so it's going to be 12 over 5 is also equal to 12. Got the inner product to be 0, but it's actually 12 5 over 5. So 10, so plus that, and then we want to do um, 12 over square root of 5, which I guess isn't. And then let's do 12 times the square root of 5 divided by 5. Okay, didn't know you could do that. Cool. Okay, and so if that's the case, then if we come back to this, it's now I need to multiply it, right? So it's now going to be 2. So 0 times 1 0 times 12 over square root of 5, and then 1 over square root of 5 times 12 over square root of 5 equals 12 square root of 5. 2 square root of 5 times 12 over square root of 5. Yeah, so I did have that right in the first place. Okay, 24 square root of 25. And then if I'm, and then that's it though, isn't it? That is the output. And so now it's okay. Let's try this again. So 0 times 0 equals 0. 1 over square root of 5 times 2 equals 2 over square root of 5. 2 over square root of 5 times 5 equals 10 square root of 5, um, plus equals 12 over square root of 5. Therefore, 0 times 0 equals 0. 1 over square root of 5 0 times 12 over square root of 5, and then equals 12 over square root of 5, and then 12 over 25, and then 2 over square root of 5 times equals 24 over square root of 25. What now? Therefore 3 therefore 3 equals 0 to 5 minus 0 12 divided by square root of 25 minus 5. Uh, take away 5. So 0.25 take away 12 square and then comma 24 over square root of 25. Therefore 3 equals something. And now I have to somehow show that 0 that show that um, show how to go from the basis with to the orthonormal basis. What now? You're on the right track. Let's finalize the computation. Given 3 equals that. I is that. From your previous computation, 2 equals that. Now to find 3, well, we did that. 0, 2 minus. So normalize 3 is. Now to normalize 3, the magnitude is. So not. Wait, so now to find 3. 0.25, 0.12 of 5, 24 over square root of 5. I didn't say that. How is it 12 over square root of 5 rather than 12 over the square root of 25? If you multiply 1 over square root of 5, if you do square root times 12 over square root of 5, doesn't that equal 12 over square root of 25? If I run the Python code, 12 divided by square root of 5, 12 times square root of 5, so 2 divided by square root of 5 plus 10. Let's try this. 1 over square root, this one, times 12 over square root of 5. then 24, 25. They're different. Okay. Sorry, I've done something wrong here. So 112. So 1 over 12. So it's 12. Yeah. If if I run the Python code, they are equal. So surely, surely you have done something wrong. What I meant was that 12 over the square root of 5 is the same as saying 12 over 5, which is another way to represent 12 over 25. Here's the calculation. Here's the clarification. 12 over square root of 5 equals 12 over square root of 5 times square root of 5 square root of 5. 12 times square root of 5 is 5. This expression is equivalent to 1225, as you correctly pointed out. Your calculation was accurate, and I apologize. Any fraction or equivalent is the correct representation. And so, if that's the case, then you've got what? From your previous computation, 0, 12 over 5, and 24 over 5. How? If I've got... Let's just eradicate this because it's annoying me. This is bullshit, no one cares about this. 2 is... So, first of all, we're doing this. Which is this. And that's... If you go back to our thing, that's 0... it's 2. So, it's 0 times 0. 1 over 5 times 2, which is 2 over 5, and then 2 over 5, which is 12 over 5. So let's imagine, so, okay, and then we have to do a multiplication of it, which is 0 times 12 over 5, 0, then it's 1 over 5 times 12 times 12 over 5, which is 12 over 25, and then which is the same as saying, it says 12 times 5, 12 times 12 times square root of 5 over 5, and then 24 would be 24 times square root of 5 over 5, And then we're going to take this away. So we're going to do and it's 2 take away 12 over 5, 5 take away 12 over 5 equals negative 2 over 5. So there must be equivalent, I just don't know it. So 0 take away 0 equals 0. 2, no, um, yeah, 2 take away 12 over 25 and 20 and 5 take away 24 over 25. They must be equal. So let's do that then. So 2 minus 12 divided by 25, and then same one is 5 take away 24 over 25 must be the same as minus 2 over 5 minus 2 minus 2 divided by square root of 5, and then minus, 1 over square root of 5. They aren't the same. Now to normalize, the magnitude is, so let's just do that. So square root of the inner product of it. So it's saying now I need to do the square root of the inner product of it. So now I've got 3 is equal to 0, 12, no, 0, well 3 is equal to that basically. Um, that's 3 there. Let's put that over there a little bit. So this is 3. And so now to normalize 3, the magnitude is, so to normalize it, it's 3 is equal to the square root of the inner product of 3. Um, so let's do that. we'll have to do, it's going to be 3x x3 equals y3 equals z3 equals, I think I just need those. So that'll be 2 minus 5 minus y3 z3. And then to do the dot product, we need to do y3 times y3 plus z3 times z3, and then do the square root of that, math.square root. Yeah, we get 0.44. I'm not sure I follow where I'm going wrong here. Um, let's call this the normalize it. And this is uh, 2 times 12 times 12 over math.square root of 25 of 5. And I'm just going to go back up again. We've got 2 2 minus, and we want, this is this part, right? So it's 2 times that. Oh, I don't know. I've just lost it. I think I need to stop. I think we're so close, but um yeah, just not quite there. Let's read on. Let's imagine that that is right, and I'm just doing something silly. Let's just read the end, and I think we'll finish there. And I'll just um clue this up at a later date or something, because it's 8:17 now, nearly 5 hours. So when we first learn about dimensionality, we associate it with a number of perpendicular directions. In this chapter, we define in terms of the maximum number of linearly independent vectors. The following theorem connects the two definitions. Theorem 4. The dimensionality of a space equals n to the negative transpose upside down t near a letter means. Yeah. So the maximum number of mutually orthogonal vectors in it. To show this, first note that any mutually orthogonal set is also linearly independent. Suppose you had a linear combination of orthogonal vectors adding up to 0. By taking the dot product of both sides with any one member and using the orthogonality, we can show that the coefficient multiplying that vector had to vanish. This can clearly be done for all the coefficients, showing the linear combination is trivial. Now, n negative transpose can only be equal to greater than or lesser than n, the dimensionality of the space. The Gram-Schmidt procedure eliminates the last case by explicit construction, while the linear independence of the perpendicular vectors rules out the penultimate option. Okay, that didn't hit like mustard, but fine. Shorts and triangle inequalities. Okay, cool. I think we'll stop there then. So thanks for watching. Made three big mistakes. So um, at least I remember. I'll try not to remember. Try remember not to do them again. But this was fun. Also tiring. Catch you soon. Bye.